Okay, so we're in Unit 4 now on counting and sequences, and this video is going to be on the inclusion-exclusion principle. We're going to rely heavily on set theory, so that would be sets Unit 2, so just keep that in mind. And I'll be recapping stuff as needed. Okay, so question. How many of the first 20 positive integers are divisible by 2 or 3? Okay, so uh, fairly straightforward question. So, first 20 positive integers, just again, that's just 1, 2, 3, all the way up to 20. Okay. So how many of these are divisible by either 2 or 3? Okay, so we could do this kind of naively and just say, well, how many are divisible by 2? So um, there are 10 which are divisible by 2. Um, so how do we get that, right? So, well, there are 20 numbers here, and exactly half of them are divisible by 2. Um, so that would be, 20 over 2 equals 10, right? And, what are they? Well, 2, 4, etc., all the way up to 20. Okay. And then how many are divisible by 3? This one's a little trickier, so I'll leave that blank for a second. So we want to do the same trick. Wait, 1 in every 3 numbers is divisible by 3. So we want to divide by 3 essentially, except that's not an integer exactly. Um, so, it's what is it, like 6 point something? I think it's 6 and 2/3. So obviously there can't be a decimal number of numbers which are divisible by 3. So is it 6 or 7, right? Do we round up or truncate down? Well, the way you can think about it is, if what's the last whole number that is divisible by 3? It's 18. Um, right. The next one would be 21, but that's outside of our domain. So up to 18, there are only 6. And so 18, so that would be 3, 6, 18. And well, there are 10 which are divisible by 2 and 6 which are divisible by 3. Therefore, there are 16 which are divisible by 6. I just add them together. But this is actually not, oops, I want to move the whole thing up. Did I? No. This is not the right answer. And take a minute to think about why. Uh, there aren't 16. Oh, sorry. I messed this up. Not divisible by 6, divisible by 2 or 3. All right. I'm not going to re-record, so let me just recap that correctly. If there are 10 numbers which are divisible by 2 and 6 numbers which are divisible by 3, then there are 16, 10 plus 6 numbers which are divisible by either 2 or 3. Right. But this is not the right answer, and I'll give you a minute to think about why. Okay. So the problem is that some numbers were counted twice. Right. Namely, the numbers that are divisible by both. So that would be 6, 12, and 18. And so if we kind of put them all in a Venn diagram and think about this, so I'll define some sets first. So define, we'll have the universal set just be all of the integers that we care about from 1 to 20. And then A will be the ones that are divisible by 2. So that we just the evens. And B will be the ones that are divisible by 3. Well, I guess I don't need dots. I could probably just write them all. Okay, so those are our sets. And if we put them in a Venn diagram, the key numbers here that we counted twice originally are 6, 12, and 18. And so then what are the other numbers that go in this? 2, 4, 8, 10, 14, 16, and 20. And 3, 9, 15. I think that's it. 3, 9, 15. And then that's it for A or B. 1, 5, 7, 11, 13, 17, and 19. Did I get them all? Let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Okay. So that's what the Venn diagram could look like. And so in this naive / incorrect way of doing it, where we got 16, what we did was, well, we counted all of the things in here. There are 10 of them. And then we counted all of the things in here. There are 6 of them. And then we added together. And then we overcounted because we counted 6, 12, and 18 twice. And so so how can we fix that? Well, we could just say, oh, we could just count and say, oh, well, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. There are 13 that are divisible by either 2 or 3. And the way we can count that just by knowing the sizes of the sets is with something called the inclusion-exclusion principle. So, uh, so just a little definition here, or recall, maybe I'll say recall, because, whoops, this is, I say eraser not working. This is defined in the book, but I just want to, so for any finite set X, if you like absolute value signs around it, that doesn't mean what's the absolute value of a set. That doesn't mean anything. But what this is just the same notation. What this means is the number of things in that set. Number of elements in X called the cardinality of X. Okay, so what we can do is we can kind of do our naive method and overcount. Um, so, but then kind of take off, like subtract what we need. So, um, right, if I take the size of A plus the size of B, right, that was just the naive way. I'm sorry. I should say what we're doing. We're counting the number of things in the union. So, right, A union B is the number of, or the size of A union B, the cardinality, is the number of things that are either divisible by 2 or 3, right? Union or, those go hand in hand. Um, number of integers divisible by 2 or 3. Okay. And if we just take the size of A plus the size of B, we get 16, but we overcounted. But we overcounted in a very quantifiable way. We just counted the intersection twice. And so we just have to subtract it off once, right? We counted 6, 12, and 18 twice. Those are the things in the intersection. So we just have to subtract the intersection one time, and then we'll be good, right? Um, so I'll say subtract intersection once to compensate for the fact it's counted twice in, whoops, the size of A plus the size of B, right? And so, uh, so we just have that fixed there. And what's cool and what's important about this formula is that it it's not just for counting divisibility of, um, of certain integers, counting the number of integers which are divisible by a certain integer, or that. It's much more broad and much more general. It works for any finite sets. So, and that is what the inclusion-exclusion principle is. So the inclusion-exclusion principle is for any finite sets, A and B. When we have finite sets, we can talk about their size or their cardinality. Infinite sets also have cardinality, but that's outside the scope of this course. Cardinality means something different for infinite sets. But for any finite sets A and B, we have the inclusion-exclusion principle, right? The size of the union is equal to the size of the sum of A and B, sum of the sizes of A and B minus the size of the intersection. This down. Okay, so that's the inclusion-exclusion principle. And, with this example, 20 integers, not too big a deal, or 20 elements in the universe, we did just brute force count to 13, right, to get all these, but let's actually use the inclusion-exclusion principle to confirm it, at least in this example. So check the previous example. So the size of A union B, the size of A, size of B. So remember, these are the things that are divisible by 2, divisible by 3, and this is divisible by 2 and 3 because it's in the intersection. So that would be 10 plus 6 minus 3, which is 13. All right, cool. Let's do another example. So another question. How many 6-bit strings start with a 1 and with 0, 1 or have exactly 4 ones? Okay. So this is a bit there's a bit more to this question than the previous one, but we can use similar ideas. So what are 6-bit strings? Well, if you've done the reading, right, they're just binary strings, so strings of zeros and ones, and there are 6 characters in a string. So how many 6-bit strings start with a 1 and with a 0, 1 or have exactly 4 ones? Okay. So we're going to try and use the inclusion-exclusion principle again. But it's going to be, we're going to have more sets to work with. So let's define A to be the 6-bit strings that start with a 1. B is the 6-bit strings that end with 0, 1. And C is going to be the 6-bit strings that have exactly, I should have probably spelled it out, 4 ones. And so, why am I doing this? Because at least now we can put a name to what we're trying to find, right? It just has to have one of these properties, could have more than one. And what we're looking for, so what we want is the size of A union B union C. right? The number of things that have at least one of these characteristics. Um, Now, what would we not want is, well, maybe we'll just, let's see, if we, if we counted up the things in each set and then added them together, that's that would be overcounting. Um, so, whoops, it would overcount. How would it overcount? Well, there would be certain things that have multiple of these characteristics, and you'd count them when you count the things in A, and then it would get counted again when you count the things in B if it's in both of them. And so, like as an example, here's here's a bit string that starts with a 1 and ends with a 0, 1. So this is in A intersect B. It's in both of them. So if you just added up all the things in A and then added up all the things in B, this would get counted twice. Um, and then uh, for another example is something that starts with a 1 and has exactly 4 ones. So let's see, starts with a 1 and has exactly 4 ones. This would be in A and C. That's an element of A and C because it starts with a 1, so it's in A, and it has exactly 4 ones, so it's in C. And so it's in both of the sets. That would also be overcounted. Um, and then another one, something that's in B and C. So a six-bit string that ends with a 0, 1 and has 4 ones. Um, oops. So this has exactly 4 ones, so it's in C. It also ends with a 0, 1. So it's in B, so it's in both. That would get overcounted. A lot of things would be getting overcounted. Our count seems to be getting worse and worse now that we have 3 sets. Another thing that could get overcounted is something that's in all 3 of the sets. Uh, so it has to start with a 1, um, and it has to end with a 0, 1, and it has to have 4 ones. So I'll just do that. So that one would be in the intersection of all 3. So this would get triple counted um, if we uh, just added A plus B plus C. So there's a lot of overcounting going on, and how to, like, in the inclusion exclusion principle with 2 sets, it was pretty straightforward. You just subtract the intersection, but here it's a little bit more complicated. Um, and let's see how we can do that. Okay, so um, let's draw our trusty Venn diagram. So I didn't say what it was, but it would just be all 6-bit strings. And then we have 3 sets here. This is just to illustrate a point. I'm not going to write all the strings in here because there are lots of them. But if we want to know what's in the union, or how many things are in the union, I should say, well, let's just start incorrectly and make adjustments as needed. So again, if we add these three, we're overcounting a lot. So first of all, when we add up all the things in A and all the things in B, we're counting this intersection twice. So just like with the old inclusion-exclusion principle, we have to subtract it off because we only want to count it once. So minus the intersection. And then similarly, when we're counting A plus B plus C, this intersection gets counted twice, once when we add up the elements of A and once when we add up the elements of C. And so we have to subtract this intersection off as well. So this is just going to be kind of like three of the two-set inclusion-exclusion principle. Now, and lastly, when we add up these three, B and C, we're accounting for when we count the contributions from B and from C, we're counting this intersection twice as well. And so so we have to subtract it back. And you might think that, oh, now this must be the answer. However, we actually didn't quite balance the budget here. We're undercounting. How are we undercounting? Well, every time we subtracted these intersections, so now I subtracted the triple intersection 3 times, because every time I took this away, I also took this away, right? And so I did that 3 times. So let's kind of just keep track of our things here. So took away the triple intersection 3 times. Well, 3 times. And when we were here, we added it 3 times. Well, if we added it right, because when we do A and B and C, right, every time we're counting this part. So we counted that 3 times. Oops. So anything, right, anything that's in here would just have been counted 3 times. And then when we subtracted, we took it away 3 times, but that means we didn't count them at all. Right? We added 3 times those contributions, then we subtracted 3 times those contributions. So we have to put it back. We have to put the right number back. So we have to put back exactly 1. And so need 1 contribution of the triple intersection. And now you can trust that that's the right count. And so it's a much more complicated formula, but I also want to kind of hint at why it's called inclusion-exclusion, because that's exactly what you're doing over and over. So you're including the single sets, then you're excluding, since you're subtracting, the double intersections, and then you're including the triple intersections. And this formula goes for any sets. It doesn't just have to be 3 sets. It doesn't just have to be bit strings. You could have 4 sets A, B, C, D, and you could have the same formula or a similar formula. But what you'd have to do is add the single sets, subtract all the double intersections, then add back all the triple intersections, and then subtract the quadruple intersection. So you're including, excluding, until you've kind of perfectly balanced the count. Okay, so we haven't answered the question yet because we don't know what the things in how big these sets are. But it's much easier to count these than to count than to try and just count from scratch. So what's the size of A? So let's do that on the next one. So remember what A actually is, the 6-bit strings that start with a 1. So if I have, like kind of an example string, I don't know how to like, let's say 1, 2, 3, 4, 5, 6. I have 6 positions to fill. The first one has to be a 1, right? That's non-negotiable. Uh, but then, and so then down here, I'll put oh, my internet just crashed. Or not my internet, my Chrome just crashed, which is where I keep my notes. Let me get that back up. Okay. Um, so I'll call this like the number of options. I'll put that down here. So for the first position, we only have one option, right? We can only put a 1 because it's an A. But then, for the next any of these could be whatever they want. 0, 0, 1, 1, 0, doesn't matter. I could just pick 0 or 1 for any of the next 5 positions. So for each of these, I have 2 options, 2 options, 2 options, 2 options, 2 options. And then if I just use the product principle or the multiplication principle, um, then then I get the answer, right? Because, after the first one, so product principle says that this would be 1 times 2, right? Because let's say, I have 2 options here. I picked 0, and then, or whichever one I picked, I have 2 more options for the next one. So it's kind of this like branching process of like um, how many options I have. Um, and it's illustrated nicely in a previous video. So this is 2 to the 5th, which is 32. I hope. Yeah. Okay, so that's the size of A. Um, the size of B, so let's remind ourselves what B is. It ends with a specific substring. So um, so the 6-bit strings that end with 0, 1. So similar argument, um, except now these I'm stuck with. So I have one option here, one option here. But then for these, I could put anything I want, right? Um, so for these, I have uh, 2 options, 2 options, 2 options, 2 options. And if I use the product principle, I get 2 times 2 times 2 times 2 times 1 times 1. So 2 to the 4th, which is 16. And then the last one, or the last single set. So let's remind ourselves what uh, what C is. This one's a bit more tricky. The 6-bit strings that have exactly 4 ones, or if you're from the book, the terminology they use is it would have weight 4. Um, the weight is the number of ones it has. So for this one, well, I don't have specific slots that like have to be certain numbers, but I do have a restriction, right? Let's just say like I want to put my 1 here and here and here and here. I don't know. And then once I've done that, once I've chosen where the ones go, the string is determined because um, I'm only allowed four of them, so the rest have to be zero. Uh, and so the number of options is going to be different, but or it's not going to be just like two multiplied together. But the number of options is, well, this is equivalent to I'm so picking four out of the six positions to have ones. This is equivalent to what? Well, picking four element subsets from the set um, 1 through 6, right? Because I pick four, like for this one, I picked position 2, 3, 5, and 6. And that subset corresponds to this string because it says I'm putting the ones in those positions. Um, and so however many of those subsets there are, that's how many um, of these bit strings there are. And these also correspond to the elements of Pascal's triangle. So hopefully the reading made that clear. But the number for that is, the notation for it is 6 choose 4, right? And there are a lot of ways you could compute this. This is, the binomial coefficient, the element in, Pascal's triangle. Um, then there's a straight up formula for it. Uh, and there's lots of ways that you can compute this. But it's, let's see. So I'm not gonna, trying to think of what was in the reading. Um, be 15, I believe. Okay. So, all right, that's a lot of work for just the sizes of these three sets. And there are how many set sizes we have to compute? There are 7 total. We've done 3 out of the 7. We have 4 more. Um, but so I'm kind of slowly with this counting part because I'll have just because the reading might have be hard to grasp, so I want to give like more concrete examples. So let's do the double intersections now. So uh, A intersect B. What is that, first of all? A intersect B, the set, is the 6-bit strings that start with 1 and end with 0, 1. Okay. So start with a 1 and, because it's in both, end with 0, 1. Okay. So this counting argument, right, we can do just kind of our little like slot diagram. And so there has to be a 1 here, and there has to be a 0 here, and a 1 here. And then I'm free to pick whichever ones I want. Maybe I go all three zeros. But the point is that I have two options for each of these and only one option for the three that because they have to be in the set. So then using the product principle again, it's 8. Okay. So what about A intersect C? That's starting with a 1 and exactly 4 ones, or weight 4. So let's draw our little diagram again. 1, 2, 3, 4, 5, 6. So, well, it has to start with a 1. Great. And it has to have weight 4. Well, it already has a 1. So um, I'm left to distribute 3 more ones among the last 5. So need to place 3 more ones in the 5 remaining slots, remaining positions. And so this is the same exact setup as with just C, where we needed to pick 4 out of the 6 positions, or in other words, pick 4 element subsets of the set 1 through 6. But now you can think of it as we're picking 3 element subsets from the set 2 through 6. And so we have a set of size 5, and we're picking 3 element subsets from it. So that's 5 choose 3. So, um, so that would be just 5 choose 3. And you could say, well, I have, one option here, and then times 5 choose 3. So technically you're using the product principle, but it's just 5 choose 3, which is 10. Okay. Last one, B intersect C. So that, remember, ends with 0, 1 and has weight 4. So if we do our little diagram, 1, 2, 3, 4, 5, 6. Because it's in B, it has to end with 0, 1. And because it's in C, I need to figure out how to distribute 3 more ones. I'll do it like that. And so I can say I had one option here, one option here. But then for this one, right, it's that binomial coefficient again, right? I need to place 3 ones in 4 slots. So 3 ones in 4 positions. And so how many ways are there to do that? Well, that would be 4 choose 3, or the number of 4 element subsets. And then if I want, I can say, oh yeah, times 1 for these 2 ones. But really, I'm just picking 3 out of the first 4 slots to have ones. And so that's going to be 4 choose 3, which is just 4. Okay. One more set that we have to compute the cardinality of, and that's the triple intersection. So A intersect B intersect C. And remember, so that has to start with a 1, end with 0, 1, and have weight 4. So start with a 1, end with a 0, 1. So for number of options, right, I'm stuck here with these three positions. And then since it has to have weight 4, I need to have 2 more 1s somewhere. So maybe I'll pick them there. But the point is that out of these 3 remaining slots, 2 of them need to be 1s. So need to place 2 1s in the 3 remaining positions. And so how many ways are there to do that? 3, choose 2. So if I really want to use the product principle, 3, 1 times 3, choose 2 times 3, choose 2 times 1, which is just 3. Okay, and so I have the cardinalities of all the sets. And so now it's just left to use the formula, right? And so I'll give it kind of as the general formula, inclusion-exclusion principle for 3 sets. Well, actually, maybe we'll just use the formula. I'll recap it at the end. So the 6-bit strings that have any one of these properties, they could have multiple of these properties, is given by the cardinality of this set, which is equal to this. And we did the hard part, which is computing all these things. So just as a recap, right, we have to add up all of the individual contributions, but then we overcounted all of the double intersections. So we want to take all of them out. But then when we did that, we took out any contribution towards the triple intersection, so we have to add that one back in. So add, subtract, add. I mean, that's it for 3, but for any number of sets, you'd alternate signs like that. Okay, so A had 32, B had 16, and C had 15. So 32 plus 16 plus 15. But we're counting certain strings 2 or 3 times, so we have to compensate for that. A intersect B had 8, A intersect C had 10, and B intersect C had 4. So 8, 10, 4. And then the triple intersection had 3 things. And so what do we get? I'm using a calculator right now. Minus 8 minus 10 minus 4 plus 3, 44. And one other thing to note, right? So how many bit strings are there total? 6 bit strings. There are 2 to the 6, so 64. So most of them have at least one of these properties. Cool. So again, just to recap, the inclusion-exclusion principle for 3 sets. So what's that? So inclusion-exclusion principle, 3 sets. So for any finite sets, A, B, C, we have the following. The things that are in any one of them is equal to the number of things in each of them minus the number of things in any two of them plus the number of things in all three of them. Okay, and that's the inclusion-exclusion principle.